Okay, beats. What is the beats? Beats is a change in sound intensity caused by the interference between two nearly identical sound waves. See these two sound waves? I'm going to make it bigger. One, it's in red, and one in blue. When they interfere, they are just kind of phase shifted by some amount. They are not in tune, right? This maximum and this minimum, they cancel. Here's maximum, minimum, they cancel. But you see some points, they both are maximum. So they create a huge, they add up here. Here, they have both maximum again, but one of that is lower than the other. So again, this is going to be a add up, right? At some point they add up, at some point they cancel, and you will see something like that created. We call this one beats, okay? Now I'm gonna read this one. So these two frequency, these two blue and red, they need to have a really close value in frequency. These two waves will demonstrate constructive and destructive interference. And this creating pattern when they interfere is like that. And from here to here is just one beat. Now, I'm gonna go to this.
Here are two identical tuning forks, both marked 288 Hertz D. If I sound them together and you listen, you can hear that they're making the same note. They're in agreement. But what if I put one in ice and the other in a flame? I'll tell you in a minute. These two tuning forks are not in agreement. This one has a little extra mass so that it lowers the frequency slightly. Now if I sound them together, you'll hear them interfering. You can see the effect on an oscilloscope. Now that the forks are...
So do you see that the previous one, they are kind of is up and down in sound, going up, down, up, down. So that would be a beat, right? If the sound is very smooth, like a beep, there is no beat. But if you go up, down, you see you will hear like a whoa, 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 right? It's going up, down, up, down. That would be a beat created. But when the sound is smooth, there is no beat. Continue watching.
Ready? Let's have a listen. First to the cold, and then to the hot. And then together. Can you hear the interference? When two frequencies are very close together, they add rhythmically, both constructively and destructively. The result is called beats. Beats, a rhythmic interference of close frequencies. Quiet, loud, quiet, loud. Wow, 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 wow. When people tune pianos, they often listen for beats as the notes get closer and closer.
Beats aren't just about sound waves. They explain why ocean waves seem to come in sets.
Surfers notice that waves come in sets. That is, small waves, then big waves, then small waves, and so on. Now that's a wave interference phenomenon. Sets are a type of beats. So watch out for beats.
So when he played the guitar, he was looking that if it is in tone and out of tone. If this is out of tone, you will see an up and down nose when you're playing the guitars, as I have to make sure it's in tune, right? Tune it. And just playing with the instrument, you will sometimes hear those beats. So it's something that you have to fix your instrument. Great. So it's here. Now, second things we want to do is the Doppler effect. So what is a Doppler effect? Let's just watch this. Oh, let's see. All right. I'm gonna show you another video. Just give me a second.
You sent in a you sent in a proposal, but your manager has so many questions.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective,
Okay, when the car getting closer to the person, it become very loud, and when moving away, it's become less loud, right? Toward the pitch increase, away from him, the pitch decrease, and the reason is that because the wavefront getting closer to each other when you going toward a person, and when it getting away, the wavefronts getting away from each other. So
the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean?
you see that it's moving toward the observatory, let's say. These are smaller, getting closer to each other compared to the wave at the back, right? Are larger. So having a more intensity of these waves together, so it's going to be louder or gonna would be blue shifted. The color will be blue shifted.
For light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards.
Okay, so if they start moving toward us, it would be appear as blue, and if they start moving away from us, it's appear as a red color, right? So, okay, there's another one I need to show you. Second Doppler effect.
You sent in a proposal, but your manager has so many questions.
Good morning. The Doppler effect is named after Christian Doppler, a 19th century mathematician and physicist who was able to mathematically describe what is now called the Doppler effect. And it sounds like this.
Perhaps you are already familiar with how the Doppler effect sounds. However, I'm here to make sure you understand why it sounds this way.
Oh, great. I always want to know why.
Me too. Actually, you know what? I do too.
All right, so it starts by recalling what this animation of a stationary sound source actually represents. So, Bobby, remind me, please.
Well,
Actually, rather than using the car horn, let's switch to a constant 440 hertz frequency being played on the speakers of the car stereo. That is the 440 hertz concert pitch which we used last time.
it's harder to hear the Doppler effect at 440 hertz rather than the car horn. Can we just stick with the car horn?
Okay, we can go back to the car horn. However, the Doppler effect is easier to understand if we refer to a single frequency. So let's keep referring to the demonstration as a single frequency, but use the car horn demonstration. Sorry, Bobby. We're back to you. You are telling us what this animation of a stationary sound source actually represents.
Right. Remember, sound is a longitudinal pressure wave,
And those lines are crests.
which are also called wave fronts.
Yeah, thanks. So sound is periodic changes in pressure in the medium, which in this case is air. Each of those lines represents a crest in the longitudinal pressure wave. That means each crest or wavefront is a location of high pressure. That periodic pressure wave transfers sound energy through the air, and the reason all those circles are the same distance from one another is because the sound source is oscillating in simple harmonic motion at a constant frequency.
And do not forget that each circle actually represents a spherical pressure wave or wavefront going out in all directions from the sound source. It is a circle instead of a sphere here because this is a two-dimensional space.
Very nice, everybody. Now remember, this animation is for a stationary sound source. Look at how the animation changes when the source of the sound is moving.
Huh, I like that.
Good, but I want to make sure that you are aware that each of those circles, which are actually spheres, represent the sound coming from where the sound source was when it emitted the sound. To make that clear, I have highlighted one of the wave crests so you can see that it is a sphere that is increasing in size, and the center of that sphere continues to be in the location where the car was when the sound was emitted by the speakers of the car. Sometimes that is a concept which gets lost in the overall understanding of this.
Okay,
Thanks.
got it.
Okay.
Now let's add a human to our animation. Notice the human, or the observer, is currently located such that the car, the source of the sound, is coming towards the observer. Bo, what do you notice about the distance between the spheres that are going towards the observer?
On the side of the car where the guy is, the circles are closer to one another.
And what does that mean?
Well, the circles represent crests in the wave, and the distance between two crests of a wave is the wavelength of the wave. I guess that means that the wavelength of the sound wave which the guy hears when the car is moving toward him is less than the wavelength of the original sound.
Correct, Bo. The wavelength of the sound heard by the observer when the sound source is moving toward them is
Okay. The wavelength become lower, right? Because these distance getting smaller and smaller compared to the normal one. The lower wavelength means higher frequency. Higher frequency means high pitch. The loudness increasing when something is the sound source getting closer to you, right? That's important.
smaller than the wavelength of the original sound. And Billy, What does that mean for the frequency of the sound heard by the observer in this example?
Okay, the observed wavelength is decreased, and you are asking how that affects the observed frequency. Well, we know the speed of a wave equals the frequency of a wave times its wavelength. That means the frequency and wavelength of a wave are inversely related. That means if the observed wavelength is decreased, the observed frequency must be increased. In other words, when a sound source is moving towards an observer, the sound heard by the observer has a smaller wavelength and larger frequency. A larger frequency sounds like a higher pitch to us, so the sound we hear when the car is coming towards us has a higher pitch.
Absolutely correct, Billy. Bobby, could you please talk about what happens when the car is moving away from the observer?
Okay, this should be the inverse of what we just talked about. Now the crests are farther away from one another, so the wavelength of the observed wave is larger. Wavelength and frequency are inversely related to one another, so because the observed wavelength is increased, the observed frequency is decreased. That is why the frequency and pitch of the observed sound are lower when the car is moving away from us.
Very nice, Bobby, but I want to specify that the frequency and wavelength of the sound source remain unchanged. To reiterate that point, please enjoy this split screen of two different viewpoints during the demonstration. On the left, you see me in the car, and on the right, you see the event from the perspective of the stationary observer. Before we heard what was happening from the perspective of the stationary observer. Now let's listen to what we hear from inside the car. The frequency and therefore the pitch you hear is constant.
Sure, the person who is in the car is not moving relative to the source of the sound, so the wavelength and frequency they observe are not affected by the motion of the car. Thanks.
But what if it's reversed and the car is stationary and the person is moving?
Great question, Bobby. That actually causes the same Doppler effect. If the sound source is stationary and the observer is moving, as the observer moves toward the stationary sound source, the observed wavelength is still decreased, and therefore the observed frequency is still increased. And the reverse is true as the observer moves away from the stationary sound source. Thank you very much for learning with me today.
Okay, so we continue after the break, and I'm trying to show you the formulations. I'm gonna stop this recording right now.